Okay, let's talk about redox reactions. So there's one more classification of reactions we're going to talk about in this unit, and that is redox, oxidation reduction. So oxidation reduction reactions occur in two parts, but these two parts have to both occur simultaneously. You cannot split them up. They can't be independent. You can't have oxidation and then reduction. You have to have them happen at the exact same time. So instead of calling them oxidation reduction, which is kind of a mouthful, they get abbreviated into redox. Red coming from the reduction, and then ox coming from the oxidation. Redox sounds better than ox-red, right? So redox makes more sense. Anyway, so basically oxidation reduction reactions are a special type of chemical reaction. In this chemical reaction, there is a transfer of electrons that occurs between two species. So basically we can track where these electrons are moving in redox reactions by using something called oxidation states. So we use oxidation states to keep track of our shared electrons. So oxidation states, quite honestly, are made up. They are the hypothetical charge of an atom. But this hypothetical charge comes from the fact that we're considering these bonds to be like fully ionic. So what would happen if our bond was actually fully ionic? Where would the electrons go? So to keep track of that, basically we assign all shared electrons to the most electronegative element in a compound. So this makes sense, right? If you had a bond that was ionic, the atom that is more electronegative is going to carry the weight of most of that electron density because it's pulling the electrons towards itself. It's more selfish than the other elements that are in the compound. So we can calculate these oxidation states according to a set of rules, and I will go through those rules with you. Just for clarification, your oxidation states can be positive, negative, or they can be zero. They can be totally neutral. Sorry, Ava's going nuts right now. We're going to put her back in the tank. So there are some hierarchical rules that we can use to justify oxidation states for different compounds. As you are going through and justifying or determining your oxidation states, if there are any two rules that conflict with each other, the overarching rule, the one that you follow, is the one that's highest on the list. So I didn't number these rules for you in the table, so I'm going to kind of number them as I go through. I split some of them up to make them a little bit easier for you to follow, even though they technically actually fall under the same rule. So the first rule is that if you have an atom in a pure element, so anything in its elemental form, its oxidation state is zero. This atom is totally neutral. So this follows rule number one. Underneath rule number one is also what the oxidation state is for monatomic ions. So mon meaning singular. So an example would be something like calcium or chlorine. If you have a monatomic ion, your oxidation state is equal to ion charge. So the oxidation state for the calcium ion here is +2. The oxidation state for the chloride ion is 1-. Oxidation states are not the same thing as like charges necessarily. These are they're a hypothetical charge. So it's not like something is actually an ion and carries this electron charge on it. They're still bonded in a neutral compound. We're just determining how much of the electrons are on that atom in the compound. Okay, so next rule, rule number two. Rule number two tells us that the oxidation states in all atoms in a compound add up to one of two options. If it is a neutral species, meaning that it's a neutral compound like the one that you see here, potassium sulfate. The sum of the oxidation states must add up to 0. However, if your species is a polyatomic ion, the sum of the oxidation states must add up to the ion charge. We'll see an example of this in just a second, but the one that you see right here, SO42 minus, this basically tells us the sum of the oxidation states for sulfur and oxygen must add up to 2 minus. Okay, that brings us to rule 3. Rule 3 says that group 1 metals in a compound will be a +1 oxidation state always. Coincidentally, this also follows their charge trend, so hopefully that helps you remember it. Group 2 metals in a compound, we're also going to call this rule 3. Group 1 and group 2 metals we can call together. This one has a +2 charge always. Again, same as its ion charge, which hopefully helps you remember it. So there are some other rules for nonmetals in compounds. Rules at the top have priority over rules at the bottom. So we're going to start off with fluorine. Then we're going to call this rule number 4. So the oxidation state for fluorine in a compound is going to be -1. The oxidation state for hydrogen in a compound, we're going to call this rule number 5, is going to be generally, most often, it's going to be +1. Rule number 6, what color have I not used it? Gosh. Rule number 6 is that oxygen in general will get a -2 charge in compounds. Now we have our last rule, rule number 7. And this is going to apply to groups 7, 6, and 5. 5, 6, and 7 if I wrote them sequentially. Things in group 7 are halogens will generally have a -1 charge. Things in group 6 will generally have a -2 charge. And things in group 5 will generally have a -3 charge. So these are the oxidation states for, or these are the rules that you can use to assign oxidation states. I will say that these 3 rules will be true for binary ionic compounds. Or for binary compounds, really, because you see CCl4, carbon tetrachloride, is a binary covalent compound. So for all other elements, what you want to do to assign oxidation states is you want to use the bonded atoms with known rules to determine unknown oxidation states. Okay, so this seems very difficult to put into practice just based on the rules, so we got to do some examples. We're going to practice by assigning oxidation states to all the atoms in the example below. I'm going to do a couple of them with you, and then I'm going to leave you to try a few on your own and check the answer key that'll be posted in our Canvas course. So to start us off, we're going to take a look at Br2. So this is elemental bromine. According to rule number 1, atoms in a pure element will have an oxidation state of 0. So that means that our bromine atoms here have oxidation states of 0, according to rule number 1. All right, next up, lithium fluoride, LiF. So here, lithium and fluorine have 2 rules. The first rule that shows up is rule number 3. Rule number 3 tells us that group 1 metals and compounds will have a +1 charge always. So that's the rule that we assign first. So lithium will have a +1 charge. According to rule number 2, the sum of the oxidation states of all atoms in a compound in a neutral species must be 0. So if lithium has a 1+ oxidation state, that means to balance it out, fluorine must have a -1 oxidation state. So that way overall their oxidation states sum to 0. Okay, next example. Let's talk about PO4. I'm going to jump over to letter E now. So PO43-, this is our phosphate polyatomic ion. So rule number 2 for this says that the sum of the oxidation states must add up to the charge of the polyatomic ion, which here is 3-. So phosphorus doesn't have a rule until you get down to rule number 7, which is the group 5 rule. Oxygen's rule shows up as rule number 6. Oxygen's rule says that in general, oxygen will have a -2 oxidation state. So, and that's per atom. So every oxygen atom in phosphate will have a -2 oxidation state. But how many oxygens do we have? 4. So if every oxygen has a -2 oxidation state, overall, the oxygens are responsible for a -8 charge in the compound. To balance that out, to get us to a 3- charge for the ion overall, phosphorus has to have a +5 charge, a +5 oxidation state. This is telling us that when we sum when we sum 5 and then the -8 from oxygen, those two numbers summed together will come out to -3. 5 - 8 or -8 + 5, either way you want to look at it, gets us to the -3. So when you have multiple atoms in a compound or in an ion like this one, you want to make sure that you're taking into account the oxidation state for each of the atoms in the compound. Okay, the last thing that I want to warn you of is letter F actually has a typo. Letter F should just be Na2S. There should be no 2 after the S right there, so please fix that one. So try assigning the oxidation states for the last 5 examples on this page, and then check in with the answer key to see how you're doing. Then come on back. Okay, so how can you find out what's being oxidized and what's being reduced in a reaction? Well, first rule, the things that are being oxidized, this is going to be losing electrons. This is losing negative charge. The things that are going to be reduced, these are your things that are going to be gaining electron density. They're going to be gaining charge. So there's a couple of mnemonics you can use to help you remember this. One of the ones that I can give you is called oil rig. So oil rig tells us oxidation is losing. Losing electrons is what that means. Rig tells us reduced is gaining. So the species that's being reduced is gaining electrons. Okay, another mnemonic I can give you comes into play on this page right here. So as some extra notes of things you need to know, oxidation always involves losing electrons. However, it does, if you listen to the name oxidation, it might imply that it involves oxygen, which actually is not true. It does not always involve oxygen. Instead, it's just talking about a loss of electrons. So another common mnemonic that you hear when talking about redox reactions is Leo the lion says grr. This comes from Leo here. Leo stands for loss of electrons is oxidation. Oops. Oxidation. So Leo the lion says grr. Grr stands for gain of electrons is reduction. So reduction always involves gaining electrons, but When you're gaining electrons, you are gaining negative charge. That doesn't mean that it's resulting in negative ions. All of our electrons are being shared in bonds. So it's not like these bonds are actually fully ionic and there's a transfer of electrons that's occurring. This isn't resulting in negative ions. Instead, it's just resulting in areas of electron density. So this is going to probably make you super angry, but the next portion of this is where things start to get a little trippy. If you have a substance that is an atom that is being oxidized in a reaction, that atom is losing electron density. So we call that atom that is losing electron density the reducing agent. Don't start screaming and shouting just yet. We'll talk through this process as to why it's called that in a second. But that means alternatively, your substance that's getting reduced in a reaction is called your oxidizing agent. So what does this actually mean? Let's take a look at an example first, because I think that's going to help you think through it. So we're going to assign oxidation states to each atom in this reaction right here to help us identify what's being oxidized, what's being reduced, what's the oxidizing agent, what's the reducing agent. So we're starting out with carbon plus sulfur yields carbon disulfide. Carbon is an element, which means its oxidation state follows rule 1 and tells us its oxidation state is 0. So I'm going to put a little 0 underneath it. Sulfur is also in its elemental form here, which means that it also has an oxidation state of 0, starting out with 2 oxidation states of 0 in the reactants. Now we go to the product. The product here is carbon disulfide. So if we want to break this thing up to figure out its oxidation states, we start with the rule that comes first. We don't get to a rule that applies to anything in this compound until rule number 7. That says that things that are in group 6 generally will have an oxidation state of -2. So in this compound, sulfur has an oxidation state of -2. How many sulfurs do we have? 2. So each sulfur atom has an oxidation state of -2. To balance that out, the singular carbon must have an oxidation state of +4 to balance out the -2 oxidation states for each sulfur. So let's think about what's happening for a second. Carbon is going from an oxidation state of 0 to an oxidation state of +4. So that means that carbon becomes less negative. That's a kind of a confusing way to think of it, but we're talking only about gaining and losing electrons here. What charge do electrons have? They have a negative charge. So it's easier to think about things in terms of gaining or losing the negative charge. So carbon's becoming less negative here. What's happening to sulfur? It goes from an oxidation state of 0 to an oxidation state of -2. This means that sulfur becomes more negative. This actually dips down into the negatives, whereas carbon goes up to the positives. So if sulfur is becoming more negative, it is pulling electron density towards itself. It is gaining electrons. It's gaining negative charge. So if sulfur is gaining negative charge, this means that sulfur is reduced. Its charge goes down. It is going negative. The charge electrons are being pulled towards it, so sulfur is being reduced in charge. Carbon is becoming less negative. That means that carbon is losing electron density. So this tells us that carbon, because it is losing electrons, it is becoming more positively charged. Carbon is oxidized. So if carbon is becoming oxidized, that means that it is losing electron density. The thing that loses electron density we call the reducing agent. Why do we call it the reducing agent? Because as it loses electrons, it allows the other atom to gain electrons. Carbon loses its electrons to give them to sulfur, so it's allowing sulfur to become reduced. So, excuse me. So carbon is the reducing agent because it is the agent responsible for sulfur being reduced. So the reducing agent here is carbon. The oxidizing agent, sulfur is becoming more negative. It is pulling electron density towards itself. It's gaining electrons. So because sulfur is being reduced, it is called our oxidizing agent. It is allowing carbon to become more oxidized as it pulls electron density towards itself. So try and figure out in this example problem right here, start by assigning your initial oxidation states, determine what is being reduced, what is being oxidized, and then determine which is the oxidizing agent and the reducing agent from that information. Then check your answer with the answer key.